Suppose we want to make an inference about mu when sigma is unknown. Remember, in previous inferences about the mean, we assumed that the value of sigma was known. Unfortunately, this is not realistic. Actually, to calculate sigma, you must know the value of mu. So if sigma is not known, what would be a reasonable substitute for that population standard deviation? Well, the natural choice is the sample standard deviation. So what effect does replacing sigma with S have on our inferences? Well, our inference now depends on the quantity t equal to y bar minus mu over S divided by the square root of n, instead of the former z equal y bar minus mu divided by sigma over the square root of n. So what effect does taking multiple samples have on the value of this t statistic as compared to the old z statistic? Well, think about which values possibly change as you take different samples for the z statistic. Y bar is the only value impacted by the sample. Whereas in the t-score, what could change? Well, there's two things: the sample mean y bar and the sample standard deviation S. Clearly, this adds more variability or uncertainty to the distribution, which describes all possible t-scores. This new distribution is called the t-distribution or student's t-distribution, and it does assume that a sample comes from a normal distribution. Look at the following graph. There are several t-distributions. There's a t with 5, 15, and 50, what are called degrees of freedom, and a z-distribution, which is your standard normal. And then these are plotted against the values of those functions, which we just put in column C1. Notice that the T5 is the solid blue line, and it has more area under the tails. Once you get past 2, 3, heading to 4, the blue curve, the solid blue curve, is higher. So there's more probability in the tails. And near the middle at 0, notice the solid blue curve is the shortest. So there's less probability piled up around the middle, or the 0 value, for the T5. As you go to T15 and T50, notice that that dashed red and dashed green line are getting taller in the center, and they're getting shorter or closer to the horizontal axis, or they have less probability as you get towards the edges, around -3 and +3, for example. And the z-curve is the purple curve that is drawn for reference. And notice with that purple curve, it is tallest in the middle out of all of them. But as the t-distribution went from 5 to 15 to 50, notice those curves start to get closer and closer to that purple curve. So what are some properties of the t-distribution? Well, as you noticed, it is symmetric and mound-shaped, but it's not a normal distribution. It has some different characteristics. The mean value, or where it is centered, is 0, just like the z-distribution. The t-distribution has n-1 degrees of freedom. Now, the degrees of freedom just tells you which curve you're talking about. It is written as df for degrees of freedom equals n-1 for now. The standard deviation of the distribution is the square root of df divided by df minus 2. This fraction is always going to be larger than 1, and a square root of a number larger than 1 is somewhere between 1 and that number you were taking the square root of. This is sort of like the sigma value in the z-curve. It represents how spread out the values are. So since df over df minus 2 is always bigger than 1, and the square root is also bigger than 1, the t-curve is going to be a little more spread out than the z-curve. Each time you select a different sample size n, you have to examine a completely new sort of table or t-distribution because the degrees of freedom are going to be different. So the degrees of freedom tell you which t-curve you're talking about. And there's not an easy way to sort of standardize or convert from one t into a sort of standard t like there was with normal distributions when we could always convert to the z-distribution. The standard deviation of the t-distribution again is larger than that of the z or the normal standardized distribution. So keep that in mind. That's one of the differences between what we have done before, always using the normal distribution and being able to convert to the standard normal or the z-curve. Now we're going to have information for each different sample size. In general, the test statistic or the t-score formula, y bar minus mu, that's the sample mean minus the population mean, divided by the sample standard deviation divided by the square root of n, is going to have a t-distribution when a random sample is selected from the population. And since we're calculating a sample mean, this naturally has to be quantitative data. The value of the population standard deviation sigma is unknown, so we estimate it using the sample standard deviation S, and either the population is normally distributed or we take a sample size of at least 30 so that the sampling distribution of the sample mean is approximately normal.